Good afternoon. So we're going to get going on our second class talking about kinetics. All right, so moving back into kinetics. We left off last time with this picture. Remember, the biggest difference with kinetics is we're now talking about the path. How does a reaction go from some initial state to some final state, and watching how fast that happens. The language of kinetics is what over what? D something dt it is. What is rate? Rate is change over time. Specifically, change in concentration over change in time. If I was to write this or express, how would I say the rate of this reaction with respect to A? What would I say that exact sort of expression would look like? Rate equals, for A, it's what? Yeah, it's, with respect to A, we're going to write D concentration A dt. If we're going to talk about with B, we'd say D B dt. The sign, though, that relates these two is what? Excuse me. That's right. dA dt will be negative. We're using that component up, and that is equal to the positive of dB dt. So they're inverse with respect to each other. You're using something up, you're forming something else. Okay. So we also talked about the fact that rate can change. If you look at this in the perspective of a reaction is running, we look at two different time points of the reaction highlighted here. Early in this reaction, we would say that here the rate is higher, here the rate is slower. Or larger rate, it's faster at this point, and slower later on. And we have a couple of ways of indicating that information. It could be the tangent of this line, right? The change in A over the same time interval is larger than later in this reaction, the change in A is smaller. Why does that happen? What's a way of articulating why we expect this makes sense?
Products are interfering with reaction.
Products might interfere with reaction, that's one. What's another one?
Less fuel.
Less fuel. You've used up A, the reaction needs A. The mathematical expression that talks about this is our rate equation, right? The rate equation is rate is equal to K times, let's say here, A. What were our other components? What did we call K? That was called the rate constant. It is specific to a specific reaction. They change with the reaction. It is the speed limit of this reaction. A here is one of the components, and sometimes there's an exponent right here. If the exponent right here is just shown as floating out, it's not given a numerical value, what does that mean? This is how, what would I say this reaction is with respect to A order? This would be what order in A? First order in A, which means if I double the concentration of A, I expect to double the rate. There's a one-to-one relationship between the concentration of A and the visible rate. So if you don't have a component, if it is missing, that what would you say that order is? If this reaction needed C, for example, and it's not showing up in the rate equation, there's no concentration of C, what does that mean the order must be with respect to C? First, second, or zero? Zero order. We could also say this equation, since that there, rate equals K times A, there's nothing else, every other component could be considered zero order. It doesn't matter. It doesn't change its rate. Okay. So, we've now talked about these general rate laws. What we need to do, so the useful thing about the rate law is if you have the rate law, you can make a guess about what initial concentration will do to how fast the reaction will go. It's a predictive equation. What we need to do, though, is redefine this. This is our differential form, the change in A with respect to time. What is useful about having this, though, is we can actually start to look at this. After we know the orders of the components, we can look at it what's called the integral form. That's a way of predicting the concentration at some future time point as long as we know what the reaction constant is. So if I start with a certain amount of A, I could use my differential form to say, well, I know how fast it's moving, how much A with this specific time. Right now, I can calculate an instantaneous rate, how fast it would go. If I say I have some amount of A, I know the rate constant, and I want to say trajectory, where will it end up? This is where the integral form is useful. So what we can do is we start here, and we are going to integrate this differential form. Remember, the differential is change in A with respect to time. From the experiment, this is something we would have to actually measure in order to get our orders. What was the method we used to actually measure or express the order in a component? What did we call it? It's one of the ones we talked about last time. How would I prove that this thing is first order in A? Yeah, it's called the method of initial rates. If I start with a certain amount of A, I measure how fast the reaction goes at that very first time point, and then I record that. I go do another experiment where I only vary the initial concentration of A, and then I measure the result of that. So you're doing a direct correlation. You're measuring, if I double A, what happens to rate. So if we have these two components, we integrate both sides, we can create what's called the integrated rate law. This is for information only, but you guys should recognize it. This is simple calculus. If I express my rate as, with respect to starting material can be expressed as the change in A as a function of time, and it's negative because you're using it up. And let's say for some first order reaction, we say it is Ka. That is the value we would have measured. From here, what we're going to do is say, okay, I want to actually express this where I'm going to separate my two differential components. I'm going to leave dA and A together. Those are my unknowns which talk about the concentration of A. And I'm going to move my dt value on the other side. Now I have all the things that are talking about time on one side, all the things that are concentration on the other. This is just an algebraic manipulation where I'm moving my dt over to the other side and moving my A over to this side. Now, if I integrate both sides, what I'm saying is, what happens? How does everything over here, this k dt equation, change over the entire time of the reaction? Everything over here is time limited. On this side, we're talking about the swing in concentration. How does A progress over that same time period? So the range of time, this is how long the reaction would happen, and the range in concentrations. That's how A goes from A0 when you start to A at any time in the future, what we call A at time t. So this is our initial concentration. This is our concentration. Oops. Oh, where's my eraser? This is concentration of A at some time t. It's a predicted concentration of A after the reaction has run for some amount of time. If we do that, and this is going to change depending on what the rate law looks like. This general form of saying, look, rate will always be change in concentration over change in time. We will always separate the two components, but depending on what the equation is, here if it's first order, it's just Ka. Integrating that component gives us this species here. That's just saying if I'm integrating this whole part, the integral of 1 over A dA gives me ln A at time t minus ln A at time 0 equals my kt. The reason for that, k is a constant. The integral of a constant returns that constant. So we just have our negative kt value. So this is our integrated first order rate law. The reason we have to underline this is every ordered equation will have a different integrated rate law. First order looks like this. Zero order will have a different rate equation and thus a different integral form. So it could be anything, but we're going to talk about three specific most common cases. Zero order, first order, second order overall, okay? So let's start with the first order rate equation. We said if we go through that integration, we get a form that we showed here, and just all we've done is rearrange it where ln AT, ln of A at some concentration T, is equal to minus KT, that's our constant bubble, plus ln of A0. Now we use that specific form because it's actually set up later graphically. This is really important. But once we have this form, you can manipulate it algebraically to any of these three at the bottom. We're taking that same equation, and remember, if you take two lns as sum or difference, you can either express it as a ratio, we can take the natural log of both sides, or we can break them up where we have these two terms. The reason these three are used is because depending on what you're trying to solve, those three different forms can be faster. If I care about k, this first one is good. If I care about maybe a0 or the ratio only, I don't have numerical values, middle is awesome. This last one, if I really want to know a at time t, but I've got all the other stuff, this one is convenient. You are given the middle one on your formula sheet, so you should be able to manipulate between all three, okay? So, how do we apply it? Let's say we have a reaction. The reaction uses bromine, Br2, aqueous, plus formic acid, that's HCOOH, to make Br minus aqueous, H3O plus, and CO2. Let's say that is the equation. We go through, we do an experiment, we solve for the rate law. Now, quick point, before we do the rest of the calculation, couple of pieces to remember. Why does the rate law look at the actual equation, the balanced chemical equation? Could I immediately look at that rate law, my balanced chemical equation, and say, yeah, I can derive that rate law from the balanced chemical equation? No. Not yet, remember? The balanced chemical equation is the total, that's like the Lego kit that tells you all the stuff you need to make the reaction happen. That doesn't tell you the mechanism or the exact path. The mechanism or path comes from those experiments, the method of initial rate, that will tell you what the order in the components are. This just says it is what order in bromine? This is first order in bromine. What is the order in formic acid? It's 0. That would have to be determined experimentally. That would have to be given to you. So we know, here's a general equation, here's the overall rate equation. So we know a rate constant. The rate constant here is given, 3.5 times 10 to the minus 3 per second. Remember, it's a first order rate law, which means the units of our rate constant are just per time, per second. If we start, Br2 is equal to 2.8 molar. When the reaction starts, what we want to know is, what is the new concentration? Where will we be after 10 minutes? So this is that predictive thing. We're looking forward into the future and saying, how do I know, given an initial concentration and a rate constant, what will the new concentration be after some period in time? You're basically going back and saying, if I had this graph, I start here, what is my new concentration here given whatever this actual value is, what expression it is, okay? So that's where we're going to use our integrated rate law. All right. So we start off by saying, okay, the concentration of A at some time t, concentration A at some time 0 is equal to E minus KT. Now again, this is that periodic chemical equation. You could choose to use any of the three manipulations that's helpful to you. I'm going to start here. We're given that K is equal to 3.5 times 10 to the minus 3 seconds to the minus 1, inverse seconds. Temperature was given as 25 degrees Celsius. Concentration A times 0 is equal to, what was it? 3.8? 2 point, oh, sorry, I'll go back. 2.8. Haven't worked out the whole double thing yet. And we're asked after time equals 10 minutes. Okay, so we've got a lot of the bits and pieces. Now, one important thing to do. In this equation, A at time t over A at time 0 is equal to E, right, raised to the power of minus KT. That little t right here, what is that t? Time. And it has to be in seconds. It is not temperature. Up until now, most of the time in experimental, right? For all of the thermodynamics, we're talking about, you know, delta G naught equals minus RT ln K, capital T, temperature. This is time, little t. So 2 parts is this time value here is not in seconds. We have to convert it. That's equal to 600 seconds. We're not going to use this point. So if we complete this out, A at time 0 is 2.8, which means A time equals T is equal to our A time equals 0 multiplied by E to the minus KT. So 2.8 E to the minus 3.5 times 10 to the minus 3 and 600 seconds. Again, the reason we're using seconds is the units on a rate constant are equal to seconds. So you have to match your time units appropriately. A here at our time at 10 minutes should be equal to 0.34 molar. Okay? How's that feel? Thumbs up? It's plug and chug, but know which pieces that you need to have, what pieces you're given, and where they go into the equation. Okay, so look at this in terms of, we've talked about before, you know, magnitude of rate constants. What do you think about this? Is this fast? 3 moles of solution, right, almost, 2.8 molar, in 10 minutes became 0.3 moles. That's a whole factor of 10 down. That is a blazing fast reaction. Have you guys done experiments in the lab at all? What were your normal initial concentrations? What's the number? I know, this is a hard, oh, right in the feels, right? But normal initial concentrations that you guys are typically, we feel safe for you guys to work with, are usually in the neighborhood of like maybe 0.3, 0.4 molar for most things. That's normal. 1 molar, you're getting there. This is a very concentrated solution, almost 3 molar, and it rips through all of that in 10 minutes. That is a blazing fast reaction. Most things are much, much slower than this, so just as far as calibration goes. So, and that's really a function of the rate constant. If I had exactly the same initial concentration, exactly the same time, what value, what should happen here to this rate constant if I wanted it to be slower? Should it be bigger or smaller? If I want the same experiment, I'm starting exactly the same amount of bromine, I'm still going to wait 10 minutes, but I want the amount of bromine left over to be higher. I want less to react. K should be bigger or smaller? What is the relationship between K and rate? If K is big, what is rate? So if K is small, rate is? So to get a smaller rate, to use up less material, I need a smaller K value. Big K is a multiplier saying how much material per unit time am I going to use up. So that's one of the things to think about. Large K values equal very fast reactions, okay? So that's our calculation. That's the part we worked through. And again, depending on the bits and pieces you're given, you may be asked to solve your initial concentration, given some final and some time. You may be asked to solve your K value, given the other components, but any of those different pieces are possible. So there's one other thing. That's the analytical way of using the rate equation, the integrated rate law, as a predictor, right, to pull out information about the reaction. The other thing we can do is what's called a graphical or a visual assessment. If I run this reaction, same case, and it was a first order reaction, this is what it would look like visually. You see you've got this curve of A falling. Remember, you're using up fuel. You've got the curve of B showing up. You're forming the product. This is the integrated rate law that applies to that. Now again, if I'm graphing concentration versus time, that's how we actually would get the experiment. The thing is, we can now choose to plot it differently. When it's in this integrated rate law form, it has the form of y equals mx plus b. By choosing different axes depending on the form of this, integrated rate law, I can choose to graph the data slightly different, and the nice thing is, it's now set up to be my y, my slope, my y-intercept, and the x value I need to plot. So by plotting ln of A on my y-axis, time on my x-axis, I'm going to get a straight line. If I get that straight line, the slope is equal to my minus k value. I can immediately extract the k just by this visual representation. I don't need to go back and do the math. I can also extract my intercept as my log of my initial concentration, wherever my concentration start of. So this is a very useful extrapolative way where if I've got this, I can now tell very quickly I am dealing with a first order process, okay? Now most important, really what's happening is if the data, concentration versus time, looks like this, it means it's obeying a function that represents this integrated rate law, which means I can graph this form of that data just by the log of my concentrations, my time values on the x. I get a different representation now as a straight line. This is useful experimentally because now I can use linear regression to solve those values. If my data is noisy or something, I can use it to extract it. It also is a very quick litmus test to say, am I dealing with a first order process? Is whatever I'm doing following first order kinetics? So if I gave you this plot, what is the first thing you can conclude? Is this a first order process? Yes or no?
No.
Why not?
Not a straight line.
Because a graph of log A versus time is not straight. That's all you can conclude from that point, but it's a quick litmus test, true or false. Is it first order? No, it fails, move on. So it's useful from that point. It just means there's other manipulation you need to do. But again, big underline, and I'll keep repeating it. This is one thing that gets a little bit weird. We use the language order in two different ways. If I have something that looks like rate equals K times concentration A, what is this reaction? What is its order in A? First, second, zero. First, right? Okay. If I were to plot the log of the concentration of A for some experiment where let's say A goes to product against time, what would I expect as long as I'm sure this rate law is being obeyed? This should look like what? Straight line, curve, and which way is it moving? Positive or negative? Straight line and always negative. Remember, your slope here is always equal to negative K. K is always a positive number. There's no such thing as a negative rate constant. Does not exist. You find one, call Switzerland, Sweden, wherever the Nobel Prize comes from, you win. Not a thing. So this must always be a negative line straight. This is the same thing as saying these two expressions are saying the rate law says you have a first order reaction, first order in A. This line says if it's a simple reaction, you are looking at a first order process. It is a reaction that follows first order kinetics. What I mean is, if I had something that looks like this, rate equals K times B, what's the order in B? So first, what if the reaction was A plus B goes to C? What must the order in A be? Must be 0. It's still first in B. There's nothing weird here. This just happens to be a reaction that is first order in B, and it follows the rate equation given. Okay, let's go to the plot. If I graph log of B versus time, what should you see? Downward slope, straight line, totally agree. Bam, right? Where again, right there, is the slope, which equals negative K. Great. What if I asked you to graph this same one, but this is log of A? Now, what should it look like? Let's step back 1 second. If I were to graph that last example, A plus B to make C, we said it follows rate equals K times B. It is first order in B. If I were to graph the concentration of anything, just any of the concentrations against time, and I could have put on here, A is going to be in red, B is going to be in purple, that's in green. All right. A, if I start here in A, what should it, this is concentration versus time. What would that, if I had to hand sketch it, what should it look like? Straight line, curvy, down, up? Right. So it's going to look something like, right? All right, product. I start with nothing. When the reaction's done, what does it look like? Curvy or straight? Does it look like it's going up or down? And it's going to look, right? Most importantly, if I sum this point and this point for every point, what does that sum have to be? The concentration of A at any time plus the concentration of C at any time. What does it have to be? It's the total. One goes away, one forms. That's what we call the mass balance. As one disappears, one forms, and that's going to be constant, right? It would be some value here, which is our concentration total, which is equal to concentration of A plus C, right? What about B? If I tried to add B to this graph, what does it look like? If I start with exactly the same concentration of B as A, that means I'm going to start right here. What does that curve look like? Does it look any different than A? It'll be on top of it. It's the same thing. It's following the same profile because they walk the same path. So the point I'm trying to articulate here, the rate law says this is a first order process. Rate equals K times B. It is first order in B, which means the graph of anything decreasing with time, any starting material versus time for that process, must be a straight line as long as you're graphing ln A versus time. If I were to graph ln of B versus time, straight line, right? That also is true if I graphed ln of A versus time, straight line. Does that make sense? I know the answer may be no. I promise I'll continue to prove it to you. Point is, if you started here, right, up in this corner, to get to ln, I'm taking the measured concentration of A, I'm taking the ln of that value at the same time point and graphing it. And mathematically, that expression shows it will decrease according to this exponential decay, meaning the log of that will be a straight line. If the two curves, A and B, are on top of each other, they must follow the same function. The point I'm trying to make is, just because you have a graph of ln something versus time being straight, that only says it is a first order process. The reaction is reacting according to a first order process. You do not immediately know it is first order in A or first order in B. All it says is, straight line, A and B are being used up according to a clock, according to a rate law that says K times something. But we don't know from one experiment which one it is. That's why we have to go back to method of initial rate. We know it's following the first order decay, but we don't know who's driving the bus yet. Yeah?
So you're saying that with these graphs and with K, it's not telling you anything about whether or not like the concentrations of A and B matter, it's just telling you the overall, the whole thing.
Exactly. You're watching a movie that is following a script that says you are dealing with a first order reaction. We don't know if it's first order in A. If you changed A, we don't know if that's going to suddenly change the initial rate, right? We have to do method of initial rate to tease out which of those two components makes the initial rate faster or slower. That is the definition of order in a component. This is a definition of order of process. I am reacting according to a first order process. Yes?
Rate law to solve for any concentration, like if it's overall first order?
Yeah, like in the end, you can use that as long as it's any first order process. Law. What you're really saying is I'm taking.
So like in this example, the rate is, like the rate is first order, but that's what you're expecting to be. You could still use that integrated rate law to solve for the concentration of A.
You could, yes, because it's still following that overall thing. But again, it's not really coming from the same place. Yeah. Like, we're taking this mathematical law, rate, and doing that integration. What I'm saying is, the reaction, put it this way, will this reaction happen if I don't have A? If I were to never give it A, will that balanced chemical equation work?
No.
It needs A to react. It just doesn't need A to go faster. That's the difference. Faster is a function of talking about the rate. Happening or not is the balanced chemical equation. Okay, again, I just draw that off for now. It's something we're going to come back to. But I want to really clearly articulate the two. Just because you plot log of A versus time does not say, oh, first order in A. Now again, if all it is A becomes B, that is absolutely true. If there's only one starting material, that's true. But if you had 5 starting materials, and then you plot any of the concentrations of their starting materials, log of any of them, and it's a first order reaction, they'll all show this perfect negative line. It just means all those 5 things are being used up according to a first order process. You don't know anything deeper from there. The reason I underline this is because 90% of the papers I review get this wrong. And these are people out there in the field doing kinetics. So I'm getting you guys ready so I never have to trash one of your articles. Anyway, that's first. Now we're going to move on to second. And we're going to look at only this special example of second. It's a second order process. It's a second order equation, but notice it's A reacting with A. It's a dimerization between 2 of the same thing. The reason we do that is because the math gets really simple. We're saying the rate is equal to minus dA dt. That's our same definition we used before. And that's equal to a rate law, K times A squared. And again, that would have been done necessarily by some other experiment. We would have measured and proved that it is second order in A. Awesome. That gives us the rate law when we integrate it. If we integrate this form, we get 1 over AT is equal to plus KT plus 1 over A0. It's this fractional form, okay? So from here, once again, with this equation, with this one on the formula sheet, at any concentration of A0 and some time and some rate constant, I can predict where my new concentration is going to be. Or, given some concentration of AT and some rate constant and some A0, I can predict how much time has happened. I can use this to manipulate and figure out where on that graph I'm sitting. Now there's one more piece of complexity I have to draw into. There's still a little bit of ambiguity in the field, and this really comes down to, again, my favorite people in the world, biologists. There's 2 different ways to look at this. Here is a concentration, 2A mix B. Does it totally make sense that the line, blue line, for A going away is steeper than the line for red coming in? Why? How would you explain that? Why is that happening?
Because they're proportional to each other by a factor of 2.
Right, the stoichiometry says that, right? You have to use up 2A to get 1B. The mass balance totally predicts this. It's fine. Nothing weird is happening here. It's just that you're doing a fusion where 2 things come together, 1 thing goes out. This is Thunderdome, right? 2 molecules go in, 1 molecule comes out. So what that means is there's 2 slightly different ways of viewing the rate. We defined first A, rate is equal to, it's a singular value, which is equal to minus 1/2 dA dt. That's, we have to use that 1/2 fraction because A is going away faster than B is coming in. So we say the loss of A is going to be twice as big as the formation of product. So we end up getting this factor of 1/2 out the front. That's what balances these 2 terms. Now you can think about this perspective. This is what we would call the true or the overall or the balanced rate. It is equating the loss of A and the formation of B, which is a single value. You can think of that also on here, where that would be the slope of these lines, right? And the slope down here at the bottom is going to be less steep, red coming in, will be half as steep as blue going away, be much more severe. But that's why we use this term of 1/2. If you use this definition of rate, you plug in this value, you get this factor of 2K1. K1 being still a rate constant, but the factor of 2 remains because we were defining it, the rate, with respect to this 1/2 A going away. We're focusing on that term of A going away, like we did the last one. A going away is this minus 1/2. If we only saw the concentration of A, and I say, I don't care what's happening with B, A going away is dA dt, therefore minus dA dt is my rate. I'm going to use this equation, dA dt, and I get another equation. They are identical. Look at their form. It's still 1 over AT, 1 over AT. 1 over A0, 1 over A0. The only difference between the two is in your rate constant. If you define the rate, and according to what we call the global, overall, where we've taken into account this doubling factor, the K value you return is with respect to the starting material going away, that half value. It looks smaller. Remember, smaller K means what for the rate? Little k is slower rate. So if we were just solving this K, what we're saying is, how fast is B coming in? That's half the value of A going away. Therefore, our overall K value has this factor of 2 associated. It's the root value of K, which expresses how fast B is coming in, sort of. K2 will just be twice as big because you never divided this by 2. You said that however fast A is going away is just A going away. Therefore, my K2 value, the equation I have here, the K, is just larger by a factor of 2. K1, 2K1 equals K2. So really what this comes to is, if I'm standing at the equation looking at my product, you're looking at 2K1. If I'm starting at the equation looking at my starting material, I'm solving K2. We will absolutely be explicit when we tell you K values here. We will be really clear about how this happens. The reason I point this out, though, is depending on if other material you go to, other textbooks, some people will live and die by this equation, and some people will live and die by this equation. I'm showing you where they both come from. They're both right. This is a perspective thing, okay? Nobody needs to go to the mat over this. Does that make sense? There's not two equations. There's just two kind of definitions of your rate, which lead you to this difference in your K value, okay? So let's apply it. If you had a reaction, 2A's become B, it follows the rate equation, second order rate equation, Ka squared, and it has a K value, and I'm telling you this K value here, this is our K here. We're going to use it as our K2. It's the K with respect to A going away as with the rate defined as dA dt. If I define my rate as minus dA dt, I'm talking about my K2 value. If I define my rate as 1/2 dA dt, I'm solving by K1 value, okay? It's with respect to which one of the two. So since my rate is minus dA dt, I'm going to be using this as my K2. How long will the reaction take for the concentration of A to reach some new value? I'm solving for time. So, we know, in this case, rate, which we said is equal to minus dA dt, which is equal to Ka squared, a second order process. K was given as 6.19 times 10 to the minus 4. And because it's a second order process, what must the units of that K value be? Remember, if it's first order, it's just 1/2. If it's second order, it's per second, and yeah, we need a concentration value to knock out. Because it's second order, it's equal to per second and per molar. That's one of the ways, if you're just given a K value and you see this concentration of in that term, it's a second order rate constant. Okay. We've got our K. We said at time 0, we started off with 1.6 molar. At time t, we have 0.32 molar. We're decreasing to this value. And what we need to find is how long is the time that takes to get to that point. So if we go back to our integrated rate law, A at time t is equal to Kt plus 1 over concentration A0. We're given all these components. We're solving for t. So if I have to rearrange that, t is equal to 1 over k times 1 over the concentration A T minus 1 over the concentration A0. Time here is equal to 4039. What unit? What unit? Seconds. That's right. Because, right there. If I wanted to express it in minutes, 67.3 minutes. So again, what equation are you applying it to? What is the integrated rate law I need? What are the pieces I've given? Do not get confused between time and temperature, little t and big T. Okay? All right. So the last thing, graphically, this is another point. We have a different form of the equation, which means I have a different y equals mx plus b. If I want to do a linear exchange or a linear portion of this, my y value is now 1 over a, not logarithm of a. My time is still time. So the y-axis has to change. If I do that, I now get a straight line, but it's a straight line with what kind of slope? It's a positive slope. So once again, if you just had these values, and this is something you may have actually done, if I've measured concentration of A, log A plotted against time, negative slope, it's first. 1 over A against time, if I plot it, and it's a straight positive line, that's a second order process in this simple form, okay? Okay, we'll pick up here from our next one to pseudo, and we'll go from there. Have a good day, guys.